All right, hello folks. Um, this is the talk on using computer vision to help stop phishing. And my name is Phil Syme. I'm CTO at Area 1 Security and one of the co-founders of the company. Before we get into it, I'll just talk real briefly about Area 1. We're a startup located in the Bay Area in Silicon Valley. And we offer an anti-phishing product for enterprises. It stops phishing in hopefully every way that the bad guys can try it. So a little bit about this talk. It's going to run about 30 minutes, maybe a little longer. And it's going to be fairly high level. I'm going to cover quite a bit of material, but at a pretty surface level. So more of a kind of a survey talk. So thanks for joining, and let's get started. So there's going to be 4 main parts to the talk. So first I'll give a background on the problem that we're solving, and I'll give an overview of the production system that uses the vision algorithms that I'll describe. I'll go into detail about the particular vision algorithms that we are using, as well as kind of what we're doing on the research side for new stuff. And then in the last part of the talk, I'll give tips about how we run these vision algorithms and other machine learning algorithms in production, and some of the approaches we take for reliability and scalability. So a little bit of background, attackers have a number of ways to try and compromise you or the company you work at. So they can steal your passwords and login credentials. They can get you to download and run malicious code. One of the most kind of virulent methods of attack they have against you is exploiting a bug in your web browser so that simply viewing a page will cause malicious code to run. And then obviously they can directly attack any server infrastructure that you or your company has and try and get control by exploiting a bug, say in a web server or something like that that's listening on a socket. And so that's how the recent Equifax hack happened. However, stealing passwords, or it's sometimes called credential harvesting, is a very effective method for hacking. It's simple, it's cheap, and it doesn't require the attackers to use a sophisticated zero-day exploit. Those are kind of hard to come by. So, obviously the process begins by the attacker sending you an authentic looking email. And the goal of these emails is to trick you into clicking a link to get to kind of a second step. And, this technique of sending authentic looking phishing emails was used to hack John Podesta in the Hillary Clinton campaign in the last US election. So it can be very destructive. Here's an example of a pixel-perfect login screen that is effective and very effective when viewed on a phone. So if you're in a rush, which is the most common way we operate nowadays, it's easy to enter your username and password in by mistake. And once you do this, the game is up. The attackers are into your account, possibly inside your employer, and it's very difficult to ever get them out again. Once they have your credentials, and they immediately start looking for more, resetting other accounts, and hiding their tracks. So the hypothesis here is for email scanning and web scanning security tools, can we use the attacker's need for authenticity against them? And, computer vision techniques are extremely effective these days. Self-driving cars and trucks, facial recognition in social media, authenticating for your phone. So, why don't we use these same algorithms in scanning software to detect logos and other artwork that are being used in inappropriate ways? And so that's some motivation for the rest of this talk and also our implementation. So in the 2 examples that I have shown so far, it's in the attacker's interest to use as high a fidelity logo or artwork as they can. And the better they do there, the easier the logo is to detect from an automated algorithm perspective. But just identifying the logo by itself doesn't solve the problem completely. So for web pages, you have to look at, obviously, the domain that the page is being hosted on to see if these logos belong. And for emails, it's a little bit trickier. You need to check the headers of the email, such as the sending IP, the actual sender and sending domain. And these things can be forged. So the problem is not straightforward. Even though emails are normally sent point-to-point encrypted these days, most of the world still hasn't adopted the secure authentication standards like BKIM and DMARC. And then in the email case, there are bulk email senders that include lots of logos all the time, and they're legitimate. So, you might think of making a model to detect the actual logos, and then a higher level model, like a model of models, to incorporate all these other signals. In our particular implementation, we have heuristic rules that we use. The model of models approach is an active area of research for us. So let's talk about extracting images. So here's an example of a phishing email. And for both web pages and HTML formatted email messages, we have a couple choices of approach logo identification. So we could render the entire email or web page in a headless browser and get a single image for the whole email, and then perform image segmentation to find the artwork and then identify them. It's an interesting note that some web pages use some pretty sophisticated mechanisms to thwart rendering them in a headless browser. They use JavaScript to try and figure out if you're a bot, and then try and dynamically create most of the page. So a great example of this is LinkedIn. I guess they've had a lot of issues with people trying to crawl them with bots. So they have a fairly sophisticated approach to make sure that only people are looking at them. So, a second and simpler choice is just fetch all the images referenced in the email or web page image tags, chase down the source argument, download the image, and just check those. Now, obviously, this second approach will fail for tiled images with small tiles. The nice thing about it is it's performant. We basically skip the segmentation problem, or at least make the segmentation problem a lot simpler. So for example, emails and web pages will often have a banner image that runs the width of the screen. So segmenting that kind of an image is much simpler. And it's actually tractable to identify when folks are using a bunch of small tiles and kind of handle that specially. So our current implementation, it takes the simpler approach for the bulk of cases. In the exceptional case, we'll take other measures. So let's just look at the system that's running this code to kind of get an overview. So I'm going to go into detail about the email scanning part of our product. And what it is a scalable mail transfer agent. So a mail transfer agent is something that serves as a middleman in email delivery. Email comes in and is processed or possibly transformed in some way. So MTAs often add headers or clean up, alter the contents of email, or they can even discard email. And then they pass it on to the normal so-called next hop mail servers. So a lot of email scanning products for businesses use this approach. As you see, we have a cluster of MTA machines behind a load balancer, so it's a very simple architecture. And these MTAs, they're stateless. They do their security scanning work and pass the email along. Now, the MTA machines have internal logic that decides if emails or parts of emails are worth asking a model about. Not all emails are interesting enough to demand processing by an ML algorithm. In the case for this talk, the logic looks for image links if they exist in the message. other key metadata to make sure that it's worth doing the logo detection. And then if it is, the mail messages are dispatched to the model cluster for logo identification. So let's look at that. So here's a picture of the model and enrichment cluster. This, again, has a very simple architecture. There's a load balancer in front of a bunch of stateless model host servers that can make a verdict. The logo identification model has algorithms to apply the vision algorithms that we'll talk about. It also has a pool of image fetching clients that are used in the case where the model is handed a set of image tags to investigate. In other cases, the model can be fed an image directly and skip the fetching pool. We have a variety of other models that we use for other kinds of malicious detections of emails and web pages and binary executables. I won't describe them in this talk, but they also live in this cluster. And towards the end of the talk, I'll explain details of why the system is architected this way. So let's get to the vision algorithms. So these days, there's, I think, two major approaches for using computer vision to identify images. The first is what I'll call the classic approach. In this approach, we work very hard to identify features in images using very clever algorithms. And I'll get into the details of exactly what I mean by a feature. But for now, think of it as just an interesting location in a picture. And so after you have all of the interesting features, you match those up with a database of reference images and their associated features to do image identification. The second approach is to use neural networks, and in particular, deep convolutional neural nets. And in this case, the net does both feature detection and classification of an image into a reference classification in one pass. So our current production implementation takes the classical approach. The big reason for this is in how these models get trained. So in the classical approach, it's okay to just have one reference image or exemplar to train on. Whereas for convolutional neural nets, you may need many hundreds or thousands, more the better, examples to be able to train it well. And so we just don't have that kind of a training set at hand. There's ways around this issue, and I'll get into some of the details about that in later slides. One thing that's interesting to note is that both the classic and the neural net approach both try to draw inspiration for the math they use from studies of the human visual system. So they both try to simulate a little bit of what our brains are doing, but they take very different approaches to do it. So I'm going to explore use of the classical approach in a little more detail now. So the first output of classical feature detection algorithms is something called keypoints. So these are the position of a feature in the picture, and they also have a direction for the feature. So think of passing a small window over all parts of the image and examining everything inside that small window or pixel patch. And the idea of a key point is to find something like a corner in these small windows that we're scanning. So we want to specifically exclude boring parts of the image. So regions that look essentially the same, and also even lines. So say for a vertical line, it doesn't change as we move our small window up and down. So to be more precise, if we take our small window and move it up, down, left, right by a small distance, if in all four cases the pixel intensities in that small window change significantly, then we want to call that an interesting feature. And the math to do this quickly and the associated algorithms are very tractable. The good thing about this approach is that those features that get picked out this way they'll be detected whether or not we move the image horizontally or vertically. I mentioned direction before. So once we have our small pixel patch, we can calculate if there's a direction where the pixels go from light to dark. So if their kind of average blending is in a certain direction, we can call out that blend direction as a direction for the feature. And so you do this by calculating the gradient of the pixels in the pixel patch, and that's a fast algorithm. The good thing about this direction calculation is that we can then flip all the features onto the side, and they'll still get detected in the same way if we rotate the image. So the last thing on Keypoints, we'd like to find features that are going to be relevant whether or not we zoom in on the picture and magnify it, or zoom out and shrink the picture. And that's called scale independence. So a trick that many vision algorithms use to make interesting features this way is to apply successive amounts of blurring to the picture and then see if the same key point detection algorithm yields the same point in the picture. In a little more detail, they use blurring. And so in the middle layer, you check to see that the same key point is identified close in the layer below, which is less blurry, and the layer above, which is more blurry. And so if it hits all three layers, then it's probably a good candidate for detection. There's a lot of really interesting technical details around the specific way to do the blurring, fast approaches for doing this kind of computation. And I put references in this slide to Surf and Sift. Those two papers are kind of the canonical ones, and also the Kaze paper, if you're interested in diving deeper on the details. Okay, so let's talk about additional information we can find about a feature. So we can do better than just identifying the location, direction, and kind of scale of a feature. We can also make a mathematical description of what the feature looks like. So this is referred to as a descriptor, or just a feature description. So this is taking our small window or pixel patch and then taking a numerical representation of all of the pixels in it. So something like, blue sky to the top right and dark sand on the bottom, but in a numerical way. So one way we could do this would be just note down all the pixel intensities in the small window, but that approach doesn't work if the image is rotated or zoomed or skewed. So David Lowe discovered a much more clever approach, and this is to reuse the trick of finding directions for a key point and use a very similar algorithm to find directions for all the pixels in the pixel patch. So a little more precisely, for smaller windows, say like a window size 8 by 8 pixels, you would record a histogram of the directions of all of those pixels, and then record that histogram all together in a single vector. And so that gives us a nice characterization of the feature we discovered. And the great thing about that representation, those very high dimensional vectors, we can use Euclidean distance to measure the similarity of two features that we have in hand. Just a little note about our implementation. So we decided to use the Kaze feature extraction algorithm. And Kaze is very similar to Sift and Surf, kind of what's been described so far, but it has a slightly different method for doing the blurring operation called nonlinear diffusion filtering. So you can see an example here of how the diffusion filtering works. The algorithm tends to combine pixels with similar intensities and together and emphasize pixels with different intensities. So it kind of turns the image into like a Lego blocks version. Beyond this different blurring method, all the other algorithms to find key points and descriptors are basically the same. Kaze is a little slower than some other methods in use today, but the performance is still acceptable for us in practice. Now that we have a set of features from a candidate image, we need to match them up with a database of feature sets, one set for each reference image. So this means comparing sets of like hundreds to thousands of features per image together and calculating the Euclidean distance between all their points. This is computationally very slow if we were to compare every pair of descriptors in each set and for each reference set sort of one at a time. So the paper in this slide introduced a method for finding matching sets of feature points, and it's called randomized KD trees. So a KD tree stores all the points in a set of descriptors in a tree format, and each branch of the tree divides all the points in the set using the single dimension of all the vectors that is responsible for the most variance across the whole set. So it picks a one variable that's going to make the best decision in terms of splitting the data. And then the process is repeated sort of all the way down the tree, each time taking the best data segmentation dimension. And in the end, this allows for basically a logarithmic search of a whole set of very high dimensional vectors to find nearest neighbors. Computing the best sort of explaining variables, like I described, is very expensive in a large data set. So there's a variant of this approach called randomized KD trees. And so at each step, you take a random sampling of all the data dimensions and use the best among that to build the tree. And then you actually build up a few of these trees, like a handful of them, using this randomized method. And then when it comes to query time, you ask them all to vote. And so this technique isn't specific to feature description vectors. It's a general data structure and approach for finding distance between any kind of high dimensional set of vectors. Okay, so let's say we have a test set of features and a set of features from an image that closely match. So many of the features in both sets are close together, and the Euclidean distance between many of the descriptor vectors in each set are close. We still could have a mismatch. So what we'd like to do is line up all of the features by their position in both sets and see if we can overlay them onto each other. And if we can overlay them, then we probably have a very good match in both sets. So the mathematical term for doing this overlay is called creating a homography between the two sets. So homography is just a matrix that we can use to transform all the points in one set to another. Homographies allow you to distort images and transform them in all sorts of interesting ways. For our purposes, we're just trying to find out if one exists, and then if it does exist, does it make sense in terms of the particular kind of overlay we have found. The classical approach for doing this is called the RANSAC algorithm. And RANSAC stands for Random Sample Consensus. Basically, you choose a small subset of points in both sets, calculate how they line up, and then you look at all the other kind of matching pairs between sets and see if they agree with the homography of that small sample set. And so if you keep randomly choosing a small subset and looking for other points in the data set that agree, you're going to quickly find the best homography between the two data sets. In our approach, we use a little more customized algorithm, kind of optimized for our use case, but conceptually very similar to RANSAC. So, okay, finally, here's the algorithm we use, kind of putting all this stuff together. So first, find all the features in the candidate image that we're looking to identify. Find the top and most similar images in the training corpus. And then try to find a homography between the candidate images and those best matches. And if we can find a good homography, then we have a match. And if we can't, then we say no match. Want to talk about the neural net approach real quickly here. Um, so, um, deep convolutional neural nets are beating sort of the best classical approaches in some cases. There's a reference data set called ImageNet that the research community uses to run sort of a benchmark competition of image classification algorithms. And the deep convolutional nets are doing the best. So I'm not going to go into details on this other than to say the early layers in the models find features sort of automatically, and they seem to find really good features. And the layers towards the end of the net do the final classification. The cool thing from an implementation perspective is the winners of these ImageNet competitions oftentimes will publish their neural nets, both the architecture and the exact weighting of all the uh, models available sort of for download and your own use. And so if you have a particular problem like this logo identification problem, there's a trick you can pull called transfer learning. And this is where you take a very good net and sort of chop off those last classification layers, add your own sort of untrained classification layer instead, and then lightly train the whole model, on your particular problem. There's details about creating sort of synthetic examples from a small set of reference logos, so you can distort them and move them, flip them around in the hopes that these transformations um, help the net be robust in its classification. This approach is still definitely in research for us. It's yielding great results, but we have not deployed it to production yet. And if you're interested in this kind of a thing, take a look at the Keras library. It makes everything I talked about very straightforward to try. So I'm going to go back again to the engineering side of the house. So when you're trying to use machine learning models in production, there's a real tension between the ability to rapidly iterate from the research side and the need to have very robust, bulletproof, optimized algorithms in production that will sort of never fail. And in our particular case, the uptime requirement is particularly strict. So, for example, in the mail processing system that I'm showing here, I mean, it has to run 24/7 with no delays, no memory leaks, no operational issues whatsoever. And it takes a lot of engineering time to make a robust implementation like that that will just never fail. And sometimes the engineering time for that can run longer than the model development time. So we try to have our cake and eat it too by putting the models in a separate process and separate machines. And the mainline data processing code calls out to the model cluster when needed. It can have, on being a client of the models, it can have strict timeouts and know sort of how to move on if there's an error response or if the response isn't in time. And then that way the model code can be built to fail fast. So if there's a small error somewhere, if it's going to segfault to run out of memory or some other kind of failure condition, we can automatically restart the model host just based off of automatic monitoring. And so that means in many cases, the ML team can deploy new models sort of at will without needing intervention from the engineers who are working on the data processing code or from the infrastructure engineers. So when there is a failure and the ML detection doesn't run, we're going to get a miss on that particular detection. And in our case, we're banking on this being rare. So say that happens once every million requests. And let's say we have a probability of one of these phishing attacks of like 1% of all the mail we see. So then if you start doing the math between those, in practice, we're going to fail very, very little and in acceptable parameters. And the other nice thing about this approach is any kind of engineering work to robustify a model can be done in parallel. The other kind of tip is that, in real life, the data that a model sees can be very messy. So no matter how hard you work on your training data sets, in practice, when you deploy a model out there, you're going to see surprises. And so those surprises are great for making the model better and for your own learning. But for a customer who depends on these results, surprises like that can be bad. So we have a couple types of feature flags that we build into the mainline code. So first, we can turn on models for specific customers. And so that means, for example, we can dog food a new model on our own company email and then roll out the model to more and more of the customer base. And the second trick that's been super useful is to run the models silently. And so that means that the models are run on the real data, the results are logged, databased, and monitored, but not actually applied to the real data flow in the end. So we can just watch what the models do in practice for a while and just make sure there's no surprises. So the incubation time for running silent, that can range from just a few minutes all the way up to a few weeks, depending on what the model's trying to do and the complexity of things. And it also means that, later, if some kind of problem comes up, you can always flip a model's vote back to off while we diagnose, but still have it continue to run to get diagnostic information. All right, and last real quick, just a quick note about a couple of easy ways you can optimize models from the machine learning team. These techniques that I've listed on the slide very much depend on the library you're using to create the model. So I just wanted to mention first PMML. So this project's been around for a while. Lets you serialize a scikit-learn model on any form into an XML format, and then load that into your own custom C or Java model runner. So that makes it easy to integrate a model into the production pipeline done by the data science team in Python or even R. And then I wanted to mention TensorFlow. So TensorFlow has the same trick sort of built in. You can serialize a model out into protobuf format along with a little text description of the model. So then you can use your ML team's work almost directly without fussing production. I've included a couple links on the slide that are just sort of jumping off points, and hopefully that can get you started. Okay, so thanks for attending the talk. I appreciate it. And go ahead and type in any questions here. So Max is asking, how fast is the system? How quickly does it do a logo identification? It's a complicated answer. I don't want to give exact times, but it's definitely quick enough to use practically. The vision algorithms that we're using are written in C, and we've done a lot of work to optimize them and make them fast. The bad part of the kind of classical approach we're taking is that the algorithm identification time scales linearly with the size of the training set. And so, there's ways to partition the nearest neighbor search algorithm across machines. We haven't had to do that, but I guess the short answer is sub-second for identification. Yeah, it's interesting. It's on modern hardware. It's fairly easy to get a fast implementation if you are paying attention to stuff like that. Thanks everybody for attending. I appreciate it.